students learn from us as a faculty. So they'll join exactly at 5 o'clock. 5, like that.
Okay.
It's always like that.
So how is the COVID control in Mumbai, sir? It's better?
But the cases are rising actually.
For the next semester, what is the plan? Your institute, they will open?
I don't know. But means probably 50%. My logic is like this: they'll open for practicals, and for theory it will go online. And this is what I think so is going to happen. I don't know exact plan of the institute, but I think they'll call students and faculty for practicals, and probably will do the rest of the things online. That's what I think so. And those practicals which are simulation based probably can be done from home also, no? But if there are practicals which require hardware, then you have to go to college. Like that. So probably student might have to go to college maybe 2 days in a week, 1 day or 2 days in a week, probably like that.
Like we are also going 3 days in a week for the time being.
But students, you which faculty are going? Students?
They are going, yeah.
The students are also going?
Students, no.
No students, that's what.
So how many PhDs, sir, you are supervising there?
6.
6 PhDs?
Yeah. Yes, 2 are over.
Okay, so your institute is having PhDs also offering, or university affiliate?
No, it's a university affiliated, but we have a research center.
University, okay. Okay, good. University of Mumbai.
Yes. Actually, it is autonomous, no? So, as per the AICT or even UGC, everything is autonomous. We can conduct our examinations, even PhD is autonomous. But then, local permission is very important. And Mumbai University is not ready to give permissions for autonomous PhD. That's the problem. That's the problem.
In your department, how many faculty are there, sir, total?
Total 14.
40.
No, 14. Our department is very small. We have only 60 UG. That's it. Undergraduate.
For UG 60 and masters?
No, we don't have masters in electronics. We have masters. We have directly. We actually closed down that in 2018. Actually, it closed down means it was shifted. It was changed to electronics and telecommunication. It was like that. Earlier it was electronics. Then college took a decision to make it electronics and telecommunication. It's like that.
Okay.
So we have actually 4 branches: electronics, electronics and telecommunication, computer, and information technology. So they are having all 4 are having undergraduate programs. Out of these 4, computer is having computer and electronics and telecommunication. They have the postgraduate programs. Yes, and PhD in computer, electronics and telecommunication, and electronics. All 3 branches.
Your institute is quite older, and sir, when it started?
So this we have. It's a different history. So we have our sister concern college called as Sardar Patel College of Engineering. It was actually opened in 1964 by Pandit Jawaharlal Nehru. Nehru opened it.
Okay.
And it was the other than IIT. That time only VJTI was the college in Mumbai, and the second college was this that was opened. Sardar Patel University.
Okay.
And then
Okay.
they started self-finance courses, electronics and computer in 1995. To 1995, actually, we were part of Sardar Patel University, SPC, and then we subsequently started information technology and then electronics and telecommunication as well. But in 2005, there was a bifurcation of the college because the government told us to separate out self-finance branches. So electronics, computer, electronics and telecommunication, information technology, these four branches were separated out, and therefore new building, new principal, everything have been established. So our appointment letter, my appointment letter is from 1999 at SPC, Sardar Patel University, and that was shifted to S.P.I.T. It's like that.
So candidates looks like a joined, sir. 10 to.
Yeah, we will wait for 3, 4, 5 minutes. Otherwise, anyway, your topic is very heavy. They need to understand. No? If they miss the beginning of the movie, then I don't know how they will reach the climax. So we'll wait for 4, 5 minutes and then we will start. Maximum 4 to 5. See, we are very particular. I know you are also particular. I am also particular about the timing. 5 means 5. But then what do we do? People don't join on time.
Today is the first date, sir?
Yeah, first day.
Starting from morning onwards, some events sessions are going?
But morning is up to 1:15 we have sessions. Then after 1:15 we take a break, and then evening 5 o'clock. It's morning 10 to 1:15, and then evening is 5 to 7.
Okay.
But then tomorrow and day after tomorrow they will have a very busy session because the demonstrations on cadence are being handled by N2P Technologies. They are the third party provider for this cadence. So their timings are very odd. They were not ready at all for 5 to 7 sessions. So they want only 2 to 4. If they want to have session, there is only 2 to 4. So then there was no choice. So we kept their sessions from 2 to 4. But then evening also we have to do some adjustments. And because there are few, if we are taking the topic, we need to have a complete overview of the mixed signal. No? We don't want to miss anything. And therefore, few topics in the evening we had to adjust. So tomorrow and day after tomorrow evening also they will have session. 5 to 6, 5 to 7.
Okay.
See, but I'm happy. Those 30, 40 they joined, they are interested candidates. And that's what we want. Right?
Okay.
Rather than having 100, 200 participants and then they are not interested. What's the point in having 100, 200 participants? Those who are joining, yeah.
So here faculty from different domains will be there, or all people in VLSI
No,
there?
VLSI.
Okay, all people from VLSI domain only.
Yeah.
That's good.
Mostly VLSI.
Okay. You can start, sir. 15 participants.
Yeah. We start. Just. Okay, good evening, everyone. So welcome for this evening session, first day evening session. And this topic is device circuit and architectures for enhancing the hardware security. To teach us for this topic, we have Dr. Ramesh Vaddi with us. And it is I'm happy actually to introduce Dr. Ramesh Vaddi. He is a very good friend of mine. And thank you, Ramesh, for accepting this invitation and part of our MDP. Thank you very much. And It's my privilege to introduce you to the participants. So Dr. Ramesh Vaddi is an associate professor at Department of Electronics and Communication Engineering at SRM University, Amravati. Dr. Ramesh Vaddi completed PhD in Microelectronics and VLSI from IIT Roorkee in 2011. He was a senior research fellow at National University of Singapore during 2018 to 19. He was postdoctoral scholar at Pennsylvania State University, USA during 2013 and postdoctoral research fellow in the School of Electrical and Electronics Engineering, Nanyang Technological University in 2011-12. Dr. Vaddi has worked as an assistant professor in IIIT Naya Raipur and Shivnadar University, India. Presently, he is an associate professor at EC Department, SRM University, Amravati. His research interests include post-CMOS devices for energy-efficient VLSI designs, hardware security for IoT, VLSI accelerators for AI edge computing. At Penn State, he was involved in Semiconductor Research Corporation, that is SRC sponsored project, Center for Low Energy Systems Technology, as well as LEAST, and NSF sponsored Nanosystems Engineering Research Center for Advanced Self-Powered Systems of Integrated Sensors and Technologies. He has published research outcomes in several top IEEE conferences and peer-reviewed international journals in the Devices and Circuits Society and has about 45 research publications and 2 USA patents to his credits. He had a few visiting research appointments and invited talks at various globally reputed institutes such as Hong Kong University of Science and Technology and Missouri University Science and Technology, Rolla, USA. Dr. Ramesh Vaddi has been a TPC member of various international conferences and symposiums such as MEDAD, INIS, and the reviewer of IEEE transactions on BioCAS, IEEE transactions on VLSI systems, IEEE transactions on electron devices, IEEE transactions on electron device leaders, IEEE transactions on nanotechnology, elsewhere microelectronics journal, Journal of Applied Physics, IOP Semiconductor Science and Technology, etc. And he is a technical committee member of several IEEE international conferences like DAC, ISCAS, ISPLED, etc. He is an IEEE senior member and fellow of IIT. So I welcome you, Dr. Ramesh Vaddi, for this session. And now I'm transferring the access slides to you. You can share your presentation slides. Welcome, sir.
Thank you, Rathod, sir. So I can share, sir?
Yeah, you can share.
Okay. Is the screen visible now?
Yeah, it has come. Clear, full, proper. Go ahead.
Okay. Thank you, Rathod, sir, for this opportunity for sharing some of my research experiences. Thank you for the introduction. So, Rathod, sir is a good friend of me. So, we both did PhD from IIT Roorkee in Microelectronics and VLSI. So, we share a good bond. So, I really take it as a privilege to, he's much senior and more aggressive researcher than me, but he has requested me to share this talk. So, I'm quite privileged to share some of my research, recent research interests, and some of our recent ongoing and some works which we have completed recently. So I'm going to give some brief into that. So this is my email IDs. These are my email IDs. So please feel free to reach to me. Sir, am I audible and clear?
Yes. Go ahead. No problem. If there's issue, I'll connect you.
Okay. Thank you, sir. Okay, sir. So please feel free to reach to me for any further future collaborations or any interests you share, common interests. So I'll be most happy to take things forward so that we'll have some joint works can be possible. Okay. So the topic for today's presentation is device circuits and architectures. So earlier I was thinking to exclusively talk on hardware security. Today also I'll be talking mostly on hardware security, but slightly I'll be touching upon energy efficiency also. So the device circuits and architectures for energy efficiency and enhanced hardware security. So most of the time I will be spending on hardware security, but around 15-20 minutes I will also be talking because energy efficiency is also one of the important aspect along with the circuits which we build. So these are the two things I'll be talking upon in today's our discussion. So the outline of the presentation is as follows. So initially I'll give a brief introduction to hardware security of IoT platform. Particularly, I'll be talking from the perspective of IoT platforms. What are the different challenges that comes into picture? Then particularly looking at the hardware security challenges and the different kinds of security issues and some overall some circuit and architectural techniques that have been proposed. So we'll be looking into some of the basic understandings and the concepts, the terminology, the section 2 and 3 I'll be talking. So after I think that we are going to spend on significant amount of time briefing the different concepts and terminology, the different upcoming emerging circuit and architectural techniques, and then in the next topic I'll be talking about post-CMOS devices, scope of post-CMOS devices for designing energy efficient and hardware secure circuits. So we'll try to have a combination of these device circuits and some of the architectural techniques. There is some demonstration, some simulation results of the work that we have done recently. I'll be sharing here. Then finally, I end the session with conclusion and discussion. And the discussion, feel free to interrupt me anytime you feel you think is necessary. So it need not be, we keep the discussion for the end. At any point of the time, please feel free to interrupt me. Okay. Thank you. So as all of us know, just a minute. So as all of us know, Internet of Things has been picking is a emerging topic which all of the programs and it has almost become like a buzzword, and several of the papers and presentations, so we'll be finding it. So here particularly I will be talking from the perspective of Internet of Things is a broader topic, so I'm not going to touch upon all the details of the Internet of Things. Here particularly what are some challenges from the point of perspective from a VLSI designer point of view, particularly for a device engineer or a circuit engineer or a circuit designer or a system designer, what are some challenges that we are going to look at? So, and then some of these challenges, particularly I'm going to talk about hardware security and reducing the power consumption or energy efficient design, how to tackle some of those challenges I'm going to present in this particular talk. So Internet of Things, like you can see a large number of, like by 2022 or 25, billions of devices are expected to connect. Several number of devices, okay, covering a broad range of applications like consumer electronics or automotive or healthcare, okay. So different fields of, and then there are different layers of the computing we can see here. There are device to that, okay, and then the application point of. So we are going to see what are some specific design challenges which the VLSI designers or the system designers will be facing. Like one is a reliability and security. Of course, two different topics, but I'm covered in one. I kept it. So reliability and security, the systems have to be obviously reliable. Okay, they need to be robust and secure in the sense here. Particularly, I'll be talking from the hardware security. Of course, there are other security aspects also will be coming into picture, but I'm not going to touch upon right now in this particular discussion. So we are going to see what are the overall security issues, and then we'll be talking about why hardware security is very, very important. And then we are going to discuss that one. So then also miniaturization. So when you have so many like devices are there, particularly when you go for applications like wearable devices, the devices needs to be, the nodes have to be very, very small. They need to occupy very, very small area. So miniaturization or low area designs. Then they have to be the power consumption has to be very, very small, ultra low power, more than energy efficient circuits. They have to be, we need to apply the techniques which we need for energy efficient techniques, design techniques have to be applied. And we try to make those circuits or systems self-sustainable. We try to harvest the power from some of the available ambient sources like photovoltaic, thermoelectric, okay, piezoelectric, etc., and try to how to power this so that we reduce the dependence on battery and the lifetime of the devices increase. So similarly, the system, so therefore, to meet these challenges, we cannot go with only one particular technology. So we need to go with a heterogeneous integration of different technologies have to go. Whichever is the best in the different things we need to go. So like one thing, like you can see a 3D IC technology. People are going for in the vertical stacking of the layers to achieve the performance. So then another challenge is like high data. The devices have to facilitate high data rates because a resource constrained application they will have limitation with the data rates. So the architecture circuits and architecture techniques which facilitate particularly the transmitters receivers which facilitate the high data rates at low energy. Okay, so it need to be developed. And then efficient storage like efficient storage, so we'll be using large number of in the cloud, like large number of and very high costly servers will be used. So the storage devices have to be very low power and very area efficient. You can track more and more amount of the data. And another important topic, of course, the is developing is using machine learning or the artificial intelligence techniques to make the devices to facilitate the on-chip edge training and the inference. Okay, first inference and then the possible training. Of course, most of the time device will be communicating, and the device communication will be taking place with the most of the computing will be taking place at the server or the cloud, but it has to very smartly decide what kind of communication, how much to optimize the resource. Therefore, there is a need for smart algorithms and hardware techniques to facilitate this kind of applications, particularly like convolutional neural networks or deep neural networks. So this is one area which we are also recently started working. It is we are very new in this some of these domains. And hardware security for the past 2 years, for the past 2 to 3 years, we have started working. So another important design, any VLSI system has to be scalable so that you go on add more and more functionality and features, and the system has to be scalable. So the next generation technology we need to incorporate more. So these are some challenges. I'm going to touch upon hardware security and minimizing power consumption or energy efficient circuit and system design. These two particular topics I'm going to challenges I'm going to touch upon this presentation. So before we look at the general any VLSI system design, okay, particularly digital VLSI system design, of course, then we'll go to analog. We need to have a few more. It will not as scale as smaller as the rapid as the digital. So we start with the different levels of like different abstraction levels will be there. The lowest like the device or the physical level. The next level will be a circuit level. Then there will be a gate level, and then so using those devices will be in circuits, and then you'll be building some basic gates and more complex gates. Then you'll be going for more modules like okay, like ALUs and processors, and then you'll go for the complete system, memories and all integration. Okay, so we are going to touch upon some of these, look upon some of these using some emerging devices. We'll try to build some of these things. So that is the reason I have kept this particular slide, which is taken from this very famous textbook like Digital Integrated Circuits, John Rabai. Okay, a very good textbook for digital VLSI designers. So if you look upon any modern computing system, if you look upon, particularly maybe you take for an IoT, Internet of Things, what are the different components that are going to be present in the system? Like you can see the devices, the basic devices that are there. Like here, these are the devices, the phone or the wearable device or the tablet or many other devices you have. There is a network, okay, or say wireless router. It is connected through, okay, connected to the this network devices, and there are on storage devices. So now in this, what are the types of some security issues can come into picture? Like one is there is the network that we are going to use. So there are issues related to network security, like denial of service or okay, some of the attacks. So there are different kinds of protocols have been demonstrated, etc. on this. Like information, the underlying information or data security needs to the different algorithms that we need to ensure that the data is not corrupted. Okay, or no information or any important information is not being confidential information is not being leaked. So information security. Then in any system, any modern computing system, you don't have only hardware. There is an underlying software which will be there, which will be supporting. Okay, so hardware, software, co-design always will be taking place. The software, so there are different levels of software security issues like software virus or file corruption or IP theft. Okay, some of the illegal access of the files or algorithms. So these are. So one important, another important thing, the actual hardware devices themselves. The hardware devices themselves, like the underlying the PCBs and the ICs and the active passive components using which the like the motherboard in a computing system. So here in this particular presentation for the next 1.5 to 2 hours, we are going to particularly look at upon only this particular hardware security. I'm not going to touch upon, so don't get confused with hardware security with all the things. Of course, some topics may overlap. Some terminology may come in similar, but here I'm not going to touch upon network security or information security or software security. Particularly, I'm going to touch upon look more deeper into this hardware security. what are the possible kind of hardware security attacks. Particularly, I'm going to talk about something like hardware Trojans. Okay, some kind of attacks like side channel attacks, slightly hardware IP theft also, some of these attacks I'm going to talk, and what are the possible attacks are the issues and possible countermeasures are the solutions. These are the two things, the focus of our discussion. How to secure the underlying hardware. So that is the that is the focus of this for the next 1.5 to 2 hours of discussion point of view. Okay. So am I clear, and any questions or doubts, any clarifications? So is it clear to all of you? What we are going to look upon, so that's what I have briefed so far.
Yes, I think we can go. Yes.
Okay. So if you try, further continuing, if you look upon the different, different layers of a computing system, as I just briefly mentioned about, this is a basic hardware, underlying hardware layer, and then there is a firmware which interface between the software layer and the hardware layer. There is a virtual machine and then operating system. Okay, stack of this is the software stack. There is an application layer, and then there is a data layer. So you can see here, like here, you can see the arrow indicates less to more. The level of difficulty, the attack difficulty, we see here. So the data is more easy to perform the steal. So the corresponding algorithms will be there in providing information security. Then the next stack will be the software security, which comes under also the network security also. Both will be joined together, and different algorithms and mostly the computer science people will be working along in those domains, how to provide the data security or the information or the cyber, like those domains. Now, one of the underlying hardware is so what we are going to see is the hardware. Usually it is quite difficult to perform this attack, but if you see here, the impact will be more. Compared to from the data to the software to this one, since the hardware is the most underlying platform on which the remaining all the different layers are being built upon, so obviously it is quite difficult to perform. But if somebody can perform an attack on that one, you can compromise the entire system attack. So the impact will be more on the complete system performance and the functionality, more of the hardware rather than of the remaining layers. Of course, it's more difficult to perform. So one assumption has been done by all the system developers recently, like for the so far, the whole concentration was on the providing the data or information security or the network security or the software security. So a large number of the people have not given much attention to the hardware security, and they assumed that the underlying hardware that we are going to use in our any system development, the different microprocessors, controllers, so the different hardware platforms, FPGA or any of the ASICs, they're like in the passive and active components of the PCBs, they're assumed to be like there are no kinds of malicious things are there. They're considered to be like assumed to be like they're safe and quite trustworthy. But with some of the recent demonstrations like happened, and I'm going to share some of those, you can see that the hardware, that assumption is no more valid anymore. So therefore, there is a need for giving more attention to this underlying layer of the platform hardware security. So therefore, it has gained a lot of interest these days, and large number of engineers and researchers and even companies, they're all started looking into what are some possible device level techniques or circuit or architectural techniques to proof their system from preventing this kind of tamperings against the hardware issues. So if we try to look at, so that is about a modern computing system and the different layers. Now let us go a little bit more closer down into. So let us more. Any questions, sir?
No,
So
go
let
ahead.
us. Okay. So now let us look more little bit down into. Let us look closer. What do we mean by our hardware? Hardware is a general. Everybody is known what and hardware. So from a, let us say here we see. Let us say you have here there is a system level hardware, maybe a thermostat or maybe some wearable device. Then if you go one, let us say there are three different layers. Let us say basically there are three different layers in a hardware. Like one is the top level system level hardware. Okay, integration of all the different components of the hardware and the processors and peripherals, everything. Then the next level you will be having different kinds of, like you look at a motherboard, the different kind of printed circuit board will be there, like some printed circuit board having different modules of the memory, some network modules, some security modules. The different modules will be there. Okay, if you look at any you open a cell phone or any of the more complex systems, you can see that then if you go down into the next level, the lowest level, where you will be seeing like different active passive components like transistors, capacitors, and similarly the different ICs, the individual ICs like controllers or system on chips, the individual ICs will be there, or memory chips, individual ICs will be there. So now we are going to see what are the different of attacks possible on different of these, each of the abstraction layers we are going to see, and the possible kind of solutions. Some attacks are possible at the lowest level, like on the direct the hardware, some possible on the like the PCB kind of, and some at the system level. Some of those we are going to look in this particular discussion. So before we, so this is about the brief introduction to hardware and particularly the computing platform, modern computing platform and an IoT kind of a system. What are the different layers present? Then we look close into the actual hardware that we are going to use. Okay. So then before we just look upon what are some of the emerging devices, I'll just give a brief introduction to about how the transistor revolution of the hardware, like they've changed. Like if you, all of us you can remember, like around 1940s, 50s, you can see the major all of our electronic systems, they're built using vacuum tubes. They used to occupy like the big size. The computer used to be the initial computer used to occupy the entire room size. Okay, so then BZTs were invented around 50s, and after that the first IC was made in around 1959. So dates are not important. So then from 1950 to almost till 1980, majority of your electronic circuit systems, the communication modules and the computing systems, the radio, the TV module, all are made using the BZT technology. And then so the advantages of the BZT over the vacuum tube is smaller area, smaller and low power consumption, and you can make more number of devices you can pack, and you can go for open door for integration. And now, as the researchers industries move toward, they started observing that the BZT is not satisfying the requirements of the further drive. So they started looking at other technologies, and then then the MOSFET technology and CMOS technology, particularly from 1980s until today, we have most of our integrated circuits and systems that are made using CMOS technology, complementary metal oxide semiconductors. Because of the small area and the low power consumption, almost zero static power. Of course, it is not anymore true. Zero static power consumption when they started, but nowadays even the static power is even consumption is even more becoming higher than the dynamic. So then few other technologies also people have looked at, like BiCMOS and those things. So this is about that one. So now we have reached to a situation where almost the CMOS technology, now if you start looking at here, like the earlier initial room size computer, you can see it is the picture of that taken. The initial computer which used to occupy the entire room size. So therefore one law which made this who predicted, like co-founder of Intel, who gave a prediction, and then later it became a Moore's law, predicted that the number of transistors that you can pack on a given die almost gets doubled for every 1.5 to 2 years. So 18 to 24 months. It's not 14, it is 24. Sorry for this. So 18 to 24 months. Sorry, I'm making small correction right now. So it gets doubled. So, and the later all the next the Intel process that came upon, they almost followed this Moore's law. Of course, slightly older slide. So they almost double transistors, the clock frequencies. You can see here like some of the previous generation of the Intel processors starting from 4004 to, you can see the initial transistor around 2300. The clock speeds are a few kilohertz, like 100 kilohertz. Now the initial processor 4004 to Intel 8-bit processor, and then 16-bit, and then you have 32, 64-bit processors. Now if you see some, of course, it is not even latest. There are up to third generation Intel processors we have. Let us say there is around 2.9 gigahertz and 1.4 billion. So we have crossed the billion transistor count on the processor given area almost in 2012. Now let us say 22 nanometer technology. Now even we are going into further smaller technology, like we have into 7 nanometer and 5 nanometer. Industries are looking, and their large scale manufacturing is going on. So that further CMOS scaling is not possible, and people are looking for alternative some kind of devices, post CMOS devices, to further continue the road of what has been done from 1940 of the vacuum tubes to BZT till 1980s or 1970, to the similar motivation is driving the VLSI designers or system, the manufacturers, to develop the next generation device platforms. Okay, so we're going to see some of those platforms, and we'll see some particular devices. Now, so that is one thing, the CMOS scaling. Another important issue that has been alarming or constantly disturbing the industries and the researchers is power consumption of the systems. So here you can see an example of some of the power consumption of the data centers of, like, for example, like Google servers. The power consumption is the data reported to be is such high that you can almost what the single data center can consume the power, you can almost run the entire power for one big city like New York that has been demonstrated. Okay, so the power you can consume that, you can save it. So therefore, you can also see there is investment on the low power circuit designs, and also large amount of the memory that they are going to use should be very low power. Okay, and also a lot of cooling mechanism people the investor has to be very, so they're quite fused the investment in that. So therefore, the researchers and the industry started this always constantly keep looking at different technologies. Like here, you can see the based on the function and the scaling, different types of devices like RRAM devices or spin transfer torque based devices. Then nanowave devices, tunnel transistors, some group 3, group 5 devices people are exploring. Similarly, some other kind of novel computing platforms like quantum computing, okay, and heterogeneous integration of the devices, and other people are looking at. These are some devices. And then you can see the 3 nanometer comparison given by this. Okay, these are the different like Global Foundry, Intel, Samsung, and TSMC. What is the possible device that going to come? Let us say still at this particular technology, what is the device that they are nano sheets or nano wires they are expecting to come to the next device to the FinFET, and then okay, gate all around device or gate all around. So these are the devices already in quite mature level of fabrication. Okay. And then novel materials, novel structures like the devices. These out of these devices, I'm going to particularly look upon one particular device that we have access to those models, and we have worked in the past 3-2 on a project. So I'm going to present some results on the tunnel FET. So am I clear so far? So I'm just
Yes.
okay. Just turning off the video for some time being. Okay, just to save band. Okay, power. Okay, so okay, I need to change it. Okay, so is it clear to all of you so far? Our discussion so far. We started with some brief introduction to the different layers in a modern computing system, kind of an IoT, and what do you mean by hardware security, and then what is the need for post-CMOS devices we have seen. Okay, so now before I move into the hardware security, for the next around 10 minutes, I will talk about using some of these post-CMOS devices. We build some circuits for energy efficient circuits we demonstrated. So I'm going to discuss that one for the time being. And then the hardware security, after the introduction to hardware security, again I will do some more simulations on this hardware security. So that I'm going to present. So if you look at here, the minimum energy in CMOS circuits is limited by the subthreshold leakage current or the subthreshold current or the leakage current, like the energy per cycle versus supply voltage. What is the smallest power supply you can use for a given circuit or a chip, or what is the minimum energy point for a given, that depend upon one important parameter called subthreshold swing. Typically for the CMOS devices, this value comes around at room temperature. It's like if you derive it, it's like 2.3 K2 by Q. It's around it's the lowest theoretical value of 60 millivolts per decade. Okay, therefore the CMOS devices have a problem in further reducing the value below the 60 millivolts per decade. So if you want to suppose these are two circuits operating, if you want to reduce, suppose you want to reduce the minimum energy consumption. If you want to reduce the energy consumption, you have to reduce your you have to reduce your power supply. Then you will reduce your power consumption, and then you will be. But what happens? The delay also will increase. To compensate one, you need to reduce the threshold voltage also. So when you are reducing the threshold voltage, so what happens? So it will increase your leakage current, like subthreshold current. If you try to remember, exponentially proportional to this one. Therefore, the leakage current starts increasing exponentially. Therefore, there is a limit on the what is the theoretical bound of the value. The practical values are obviously will be higher than the 60 millivolts. Like you have around 90 to 100 millivolts per decade only. You will never be able to reach the 60 millivolts per decade. But remaining all, but it's a very theoretical bound limit. All the CMOS circuits will be having higher than this value. Okay, so therefore the researchers and the industry started exploring some alternative steep switching, steep subthreshold slope devices or steep switching devices. So like devices like where the switching will be from on to off will be steeper. So the subthreshold swing value, how do you define subthreshold swing? The minimum gate to source voltage that is required, the VGS, to bring a decade change in the current. So if the smaller this value, I can make the device turning from off to on or on to off in a more faster manner or more steeper manner. So some devices have been identified like tunnel FETs, negative capacitance FETs, some nano electromechanical FETs or NEM relays. Okay, these are some devices have been demonstrated, and of course more new devices are coming right now recently. Some hyper FETs and some ferroelectric and negative capacitance NC FinFETs. Some devices are coming there. So these are the typical subthreshold swing values of the decade values. Of course, some values are theoretical simulation, experimental values could not be achieved, some of them. Okay. So here in this particular discussion, I'm going to revisit upon one particular device, a tunneling FET or tunnel transistor, which I'm going to repeatedly use this for some simulations. Some simulation results, I'm going to use this device. We have download. Okay. So what do you mean by tunneling FET? So this tunneling FET, here, if you try to look at the basic MOSFET, here there the mechanism is the carriers, they move around the barrier. So the inversion takes place. Here the barriers will be so low, so close to each other. So instead of the carriers cross over the barrier, they just tunnel through the barrier and they involve band-to-band tunneling. And that makes us help this operating voltage taking place at a very smaller voltage. Okay, so one of the important, so the subthreshold swing values have been good values have been reported, but one problem the researchers and the experiment industries were facing, the consistent in the on current value. The simulation values are get value, but they're not able to achieve the subthreshold swing value over several decades of the current. The circuit you need to operate at over several ranges of supply voltage. So these are some issues they're facing, and they're looking for some combining one or two of some of these devices. Like they're looking for negative capacitance and tunnel FET they're trying to look at how to achieve further. So therefore maybe they're trying to replace the materials that are not the silicon tunnel FET. They're looking for some group 3, group 5 materials using for building, so that some heterojunction tunnel FET, some of those combinations the industry people were exploring. So when we started the work like around 3-4 years back, this tunneling transistors was in a quite this one. So at that time we designed some circuits. So these are some simulation results that we have done. These are the models that are available from this group, like on the NanoHub, all of you must be knowing NanoHub. There are some models are there available. They keep a repository of the models developed at different groups. Like in the Penn State University, while I was there, this group has developed 2 models. Those models were used here, and also those models are available in the NanoHub also. So now this link has been moved to that particular NanoHub completely. So what we have done, any particular device you are going to use, first thing we need to benchmark its performance. How good is this particular device comparison to the existing some of the industry standard present, the best device that we have. So at that time we have taken a 20 nanometer tunnel FET. So we try to benchmark with its performance with the 20 nanometer FinFET device that is available. The model is available, and both the similar the models are available. So the LUT based Verilog models are available, and we try to put those models in cadence environment. We created a library. The models, okay, just symbols created, NMOS and PMOS. The models are kept in the back, and we try to use those models to build our circuits. Like we started building like inverters and all complex circuits that we are going to see in the ahead. We have built some of all those circuits are built using in the cadence platform only. So there are 2 models we used basically. One is the models from Penn State University, which are available in the NanoHub platform. Another is there is one more group like North Carolina State University. They also have some developed models. Those 2 models basically we used for our simulations. So here we try to, so this device is a double gate heterojunction tunnel FET, and the reason we heterojunction, the junction here and the junction will be differing. So first we try to compare its ID versus VGS and ID versus VDS characteristics, and then try to extract the subthreshold swing value. So for a given change in the VGS value, what is the change in the decade current? So we have observed that, as we have seen, so the subthreshold swing value for the tunnel FET is around 30 millivolts per decade. For the FinFET, for the equivalent FinFET device, it is around 60 millivolts per decade. And now these are some of the tunneling transistors have some unique device characteristics I will be going to discuss. Like they have some unidirectional conduction. They conduct like it is an asymmetrical device. Just like the normal MOSFET, if you interchange the terminal, it will be working. But this heterojunction tunnel FET is like a unidirectional device, so there are some challenges that comes into picture also we are going to use. So we try to benchmark like the heterojunction device with a homojunction. Suppose both the junctions are same material, then heterojunction. So we have observed that the heterojunction tunnel FET will be having a smaller subthreshold swing because of the reduction in the effective barrier, and so therefore the subthreshold swing is one important parameter. On current, off current, then on to off current, and then for digital these parameters are sufficient, but for analog we need to have important other parameters like GM, transconductance, and then GM by ID, effective transconductance like GM by ID. For a given bias current, what is the transconductance that you can achieve? Okay, then figure of merit, because device needs to be suited for analog, not only digital, it needs to be suitable for analog. Then only you can build some mixed signal applications. So therefore the figure of merits we have measured also for some GM by ID and FOM. So we observed that the heterojunction tunnel FET devices at a given supply voltage less than 0.5, the on current has been reported to be like around 10. Of course, these are simulation values. We need to take these values with a pinch of salt. So it's not, we need to be okay. So then approximately 10 times the improvement in the on current. And the overall improvement in like the GM by ID values around 3 times improvement in the GM by ID values, and the unity gain frequency 7 times. Okay. The overall figure of merit, device figure of merit has improved. Now some of these metrics will translate into some circuit performance metrics you can see here. Like here you can see, of course, anytime you take any new device, you always, like the new device, always the first few digital circuit that comes into picture will be our inverters and logic gates. So we started building some few logic gates. We started building few inverter and then DC transient characteristics. We try to simulate how the robustness of the characteristics and the noise margins. And then we try to see the transient characteristics and the low propagation delay, high propagation delay, the total propagation delay, and then power consumption, total power and delay and the energy. Okay. We observed that more than 50% of the tunnel FET based circuits observed to be more than 50% energy efficient compared to the equivalent tunnel FET device at the given supply voltage. And another important thing, as we are scaling down supply voltage, the FinFET based circuits started deteriorating in the functionality, but the tunnel FET, the device characteristic even up to 0.1 volts, they are working still intact. So therefore they started exhibiting to, because of the smaller subthreshold swing value 30 millivolts per decade. So even for smaller supply voltage also you have a significant amount of the drive currents you are able to achieve. Okay, so therefore so that was observed. Now, as I mentioned, the tunneling transistor is a new device, and there are some every device. It's not that always have some advantages. There will be some challenges, or the challenges will be there. One difference from the MOSFET will be it has a unidirectional conduction. It is an asymmetric device. It's not like the normal MOS device. It's an asymmetric device. So if you interchange the source and drain terminals, it won't work. So the source and drain terminals have to be properly connected. And then it's a unidirectional. Therefore, it is a unidirectional device. And also there is the pin forward, when the device is like a forward, supposed to be off, but it still conducts some important current, pin forward current. So these are some challenges in the design using these devices into. And one more important device consideration is the on-state Miller capacitance effect is quite larger here. When the device, therefore, when you see here, there is a on to off, but okay, there is a devices. When okay, there will be some glitches you will observe, or some peak overshoots and undershoots will be observed in digital circuits. So if you don't apply proper techniques, so what can happen is that the circuit that we build will be having large number of timing errors and glitching, and power consumption will be quite larger. So therefore, we started looking, then further we started building some more circuits like buffer circuits, ring oscillators, okay, for different supply voltages and different load capacitances, okay. We try to build some adder circuits also, and then try to compare the power consumption, energy consumption of some of these devices. And we observed that for the same circuit of a tunnel FET and FinFET we are comparing, we were able to extend the operation like here, sorry, like energy consumption you can see here. As you are increasing the load capacitance for a given size of the beyond certain load, the FinFET device is not able to drive the more loads. Okay, whereas the tunnel FET device is able to drive this one, even increased loads also. So the robustness or the the robustness of the circuits is much better than the equivalent FinFET devices, because of the steep subthreshold swing and therefore the larger on to off current ratio, and the device can drive more effectively. So as I mentioned, the previous some of the devices have some drawback. I mentioned the overshoots and undershoots. Like here in the ring oscillator circuits, you can see the tunnel FET devices when they're oscillating, there are some peak overshoots or undershoots or glitches are there. So therefore, what we have done, we try to use some circuit technique. Like this one is a normal static CMOS circuit. We try to use a design using a differential technique. Okay, this technique. I try to see that this ring oscillator design has reduced the the glitches that are present in this one. Now you see the ring oscillator here. You don't find the glitches that were observed here. Okay. Of course, there is a small compromise in the operating frequency has been reduced because of this. Okay, the energy efficiency also has been reduced, but we're able to minimize the power, like here the glitches here in this particular design. The frequency of oscillation versus supply voltage, like here the range you can see here the tunnel FET ranges. You can see a tunnel FET ring oscillator and the FinFET equivalent FinFET design. So those are some kind of digital circuit that we have built. Now, this is one kind of work that we have done like during our Penn State University work. This work actually we have got the US patent. We try to build some rectifier circuits using these tunneling transistors. So since the tunneling transistors, like if you try to see the power conversion efficiency versus the input RF input power, most of the CMOS rectifiers, they have quite good high power conversion efficiency values at smaller RF input, at large RF input power or strong signals. The RF input power levels are very, very small. What we observed is that the conversion efficiency values are even less than 20%. So therefore, we try to exploit whether we can see whether the transistors perform, the tunnel FETs perform better than these devices at this region. We try to explore, and we have demonstrated that we are able to exploit some of the unique device characteristics of tunnel transistors into an advantage, and we'll build some rectifier circuits, and we demonstrated that these rectifier circuits that we design have more power conversion efficiency and better sensitivity. The signals can start responding to smaller RF input powers with higher efficiency, so that therefore the deadband that reduces and the sensitivity or the range can be increased. Suppose you are using passive RFID rectifier, so it will increase the range of the tag. So the range of the communication can be increased by using this one. So that's what we have gone into this patent. Done one. Okay. So then we try to extract the different parameters for. Of course, these topologies are the conventional normal CMOS topologies, but we try to use the these tunneling transistor FETs, and we try to demonstrate some of these circuits. So that is about the emerging transistors, like tunneling transistors for designing some energy efficient circuits and systems. So I did not talk about the hardware security. So I'm going to show some results more using tunneling transistors for hardware security. So before that one, I will spend some significant for the next. We will have around next 30 minutes around. We'll be spending the different terminology and issues related to hardware security. Any questions or clarifications? Any doubts?
Anybody wants to ask any question? Dr. Ramesh, I would like to ask something.
Oh, yes,
I would like to clarify something. So when we talk about this hardware security, so are we talking about the actual protection of hardware? That is, somebody wants to attack to the hardware and destroy the hardware kind of thing, functional destruction of functionality, something like that. Or we are trying to protect our hardware from like an intellectual property, like somebody should not copy our hardware.
No, actually, those are both things comes into hardware security. Like the IP piracy or reverse engineering is one kind of attacks. Now another kind of attacks also, like you're saying, like there are some invasive attacks and destroying, and those attacks also we're going to discuss.
Acha, both are part of that.
So those are everything related to protecting the hardware. Like hardware needs to be protected from either from piracy or reverse engineering kind of attacks, or maybe any possible malicious intention modification of the hardware, or any kind of side channel parameters information. So all these kind of will comes under hardware security.
And one more thing is, since you have discussed the tunnel FET transistor, so because generally we will have our basic MOSFET based circuits, and what is the motivation for selection of tunnel fit transistor? Because I think using that only now you will be demonstrating other things also.
Yeah. Basic motivation is it is a steep subthreshold transistor. Okay, transistor which can achieve a subthreshold swing value less than 60 millivolts per decade. Okay, so that means you can operate at smaller supply voltages and you can achieve higher, better power consumption. You can reduce the power consumption and energy efficiency, all those values.
Achha, achha. Because your aim is to use them in the IoT node. That's the reason.
Yeah. So actually, we started showing only some simple like circuits, adder, and later I'll be going into some kind of more circuits. Like we had done some analog circuits, like we also did some PLLs, we did some analog like amplifiers, differential amplifiers, some 3D IC circuits we have done. So we have touched up like
No,
different.
because what I was thinking that security at device level means what? That means robustness of device, and what exactly? How do you protect the device?
How do you
Which
protect a
will be
device?
good?
Okay. So I will be touching upon some kind of attacks which are possible, like at the device level, like people can tamper with some of the layer, like masks. The modification, the mask parameters, temperature modifications. So some of those I will be talking. Protecting the device itself, like the tunneling FET device. What I'm going using the tunneling FET. I'm going to demonstrate some circuit techniques, like combination with some circuit techniques. I'm going to demonstrate some applications. I'm going to see how the whole system can be protected. That I'm going to demonstrate.
Okay. Go ahead. Thank you.
Okay. Thank you, Rathod.
I think somebody has asked a question in chat box. Yeah, can you read? If you can, it is okay.
No, I'm not able to read, sir, that one because.
Okay, I'll read. I'll read.
Okay.
What I understood from your introduction is you are going to explain the architecture features of devices that are used in hardware security applications.
Mm-hmm.
Am I right?
Yeah, I'm going to touch upon the. Sir, once again. Sorry.
See, I'll read again. What I understood from your introduction is you are going to explain the architectural features of devices that are used in hardware security applications.
Yeah, you were partially correct, but partially not. So I'm going to touch upon architectures of devices, not all devices I'm going to touch upon. I'm going to touch upon device techniques, some emerging device, and some circuit and architectural techniques in joint combination, how to build some kind of a system which make your complete system more secure. So that I'm going to build, I'm going to demonstrate.
Okay, go ahead.
Okay. So before we move into, okay, thank you. So before we go into, now let us have some basic familiarization with some of the terminology related to hardware security and the different kinds of attacks and some usual kind of countermeasures. And out of these few countermeasures or techniques, I'm going to apply and demonstrate using the previous tunnel transistors. Okay, so that will be the roadmap for the roadmap ahead for the next 1 hour. Okay, we have. So here we'll try to discuss like what are the different design challenges, and then what are the different kinds of techniques. Some are circuit and architectural techniques, and some will try to use some of a combination of these techniques and the previous device techniques to build some more secure primitives we are going to demonstrate. So the hardware security challenge, you can see, as I mentioned, the underlying hardware, it's considered to be like a secure. The devices, active passive devices, the ICs, okay, all the components, no, but there are methods to test the functionality or manufacturing defects, but there are no presently the tools or the platforms available to check the authenticity of the device that are there. Okay, so those are not available for the time being. And recently it has been demonstrated that like a large percentage of counterfeit ICs are there in the military supply chain. And also some of the hardware that going to use like the different kinds of attacks like hardware Trojans. Okay, so these reverse engineering some of these kinds of attacks. I'm going to some reverse engineering and side channel. Some I will be elaborating more as we move into some of these slides. Like one kind of attacks like here, side channel kind of attacks. Okay, the possible kind of attacks. So I brief upon that. So here, what some of the adversaries or the attackers they try to do, they don't try to actually attack the algorithm that is there, the actual. So what they do is that the surrounding environment based on studying some side channel parameters like the power consumption. Power consumption generally what happens depending upon the data that is running inside, the power consumption, the profile will be varying. The particular the current, the supply voltage is fixed, current will be varying. So for over a period of time, you collect the different traces of these powers, and then you apply some algorithms that you extract the key, and then you can steal the what is the function that is there that you can do. Then you can steal the particular you can break the security of that particular architecture. So that comes, and so that is one kind power based attacks. Now similarly, like you can listen to the every device when it's functioning, there will be some kind of radiation. Okay, the radiation patterns will be different, the radiation profiles for different operation. When the same processor doing, let us say it's doing a arithmetic operation, that is a floating point operation, or okay, when it's doing a convert, so the power the profiles will be different. So that comes under this EM or electromagnetic kind of attack. Similarly, there are some kind of attacks like delay based. So therefore, these are some kind of attacks that comes into picture. Therefore, more focus was on developing making the algorithm secure. That was the whole focus of the most of the system developers. They did not give attention to some of these kind of side channel, but recently they were started giving more attention. Okay, so I will touch upon some of these like side channel attacks, like some of these techniques I'm going to brief, okay, shortly. So the example attack, some kind of attacks, of course, I'm giving an overview about the different kinds of hardware security attacks, and then I will narrow down to some of the particular kinds of attacks which you are going to implement, and then some solution that is the plan for the next minutes we have, the time we have. I'll give an overview about the different kinds of hardware security attacks from at different levels or different layers, and then we'll go on to the particular one kind of a few of those we'll be looking at.
Sir, I want to ask one thing actually. Hello,
Yes,
sir.
please. Yes,
I
please,
said
please.
that previous slide now I didn't understand that PUF and TRNG means solution.
Yeah. Actually, I'll be coming to this one. PUF actually indicates physically unclonable function. PUF. So what exactly this one I'll be elaborating in the next one. That's why I did not touch here. I'll be coming in the next few slides. Okay.
Okay, sir. Okay, sir. No problem.
For the time being, I'll mention PUF means physically unclonable function, and TRNG means true random number generator. Okay.
Okay, sir.
And how they will make the system secure, that I'm going to touch in next few minutes. So like some of the attacks, like you can see here, like there was a demonstration, like Israel, there's a attack on the nuclear facility in the Syria. So what was some of the suspects, the state of the art radar supposed to alert the system, it could not, it failed. So the people have after thorough analysis, they predicted that some of the commercially off the shelf microprocessors that were used in that radar, okay, there was a compromised IC, the microprocessor was introduced, and that was programmed to fail at a given time. So therefore, when a given time was there, the particular that radar supposed to alert that microprocessor has failed and could not do the alert. So this is one kind of an attack that was demonstrated. It's slightly older, but this is one. Okay, so they have used some kill switches to disable that function, so that when it's supposed to alert the like a fire alarm or particular alerting, it gets stopped that one. So then somebody adversary can do that attack. Similarly, there is an increasing kind of some kind of compromising the hardware platforms like fake Cisco routers. Okay. So as per these investigations of the S.P.I., you can see that the fake routers were there in the large part of the American networks, which have been imported from some kind of countries like China. So it was as per their data and statistics. So they were costing around $76 million of fake Cisco routers. Okay. So so annotation. Okay, so this is the fake Cisco routers. So they're costing around this much. Now, energy theft from going backwards. Now, like most of the country, they're going from the conventional grids to smart grids. They're going to use smart energy meters and the network, all those things. So there has been a recent several demonstrations of like there is a project in the UK. They have demonstrated like using PUF. They have tried to build one energy meter which is more secure than the conventional. So the energy thefts are going. So the smart energy meters that are there can be compromised. So they were also costing several $1 billion to the companies of these they were doing. Okay. Then there was one professor, Princeton University professor. There was one revelation by the professor. He says that there is no much security to the hardware, underlying hardware that is used in the electronic voting machines. So what he says is that the underlying read-only memory chip that were there, which are used to hold the program instructions for counting votes, they were not properly soldered. So anybody who has access to the hardware, they can replace that ROM with the another programming that one. Of course, it was rejected by the company which sponsoring those like Sequia, which is managing the elections for several years, like 1460. They claimed that the process analysis was bogus, and because the machines bought off the end, they were slightly different. But there is a possibility that was demonstrated that these hardware, that underlying hardware, is not fully secure. There is a possibility of because basically you are using a hardware which is there's a potential for compromising that. So that's what this claims, and there are this particular link, if you interested, you can have a more look into this. The particular professor demonstrated some kind of algorithm, some demonstrations gives that there are how he has done particularly some kind of on this they have demonstrated. So similarly, like some kind of attacks, like recently some of the smart cards, like physical attacks were demonstrated on the chip IDs, like they try to extract the secret keys. Some kind of attacks like physically damaging the devices, delayering of the devices and extracting the layout, and then reverse engineering to understand what is the functionality. So then the second one is like a side channel attacks, like different side channel parameters can be extracted and the key can be extracted, tampering with the electronic devices, and then and some counterfeit IC is using. So I'm going to touch some of these. Like smart card is some attacks recently demonstrated. You can read upon more of these. I'll be sharing these slides after my talk, so people can look more into some of these. You find anything interesting, some videos are there in that, so you can have a more look. Like smart cards under attack. Like, so another one of the compromising or tampering in the hardware is IC counterfeiting. So it is one of the most prevalent attack today, and it has been there for quite large amount of time. So unauthorized production of the wafers and the ICs, and it's estimated that the counterfeiting ICs is costing the semiconductor industry all of it's $1 billion. We see in our country we have only a few places, like in there is 180 nanometer in ISRO has 180 nanometer. SCL Chandigarh, they have one fabrication unit. The rest of that, we don't have much large scale in India, because it's quite $1 billion investment needs to be done for fabrication of ICs. So therefore this is costing a lot for the semiconductor industry company, because some people who have some access to some of those these ICs, they are compromising, and they're making at cheap level, low cost, some of the ICs which are actually genuinely produced. So that we are going to look at some of these, like cloning of the ICs or overproduction, defective ICs they are going to use, like that. So the counterfeit electronic parts are like it is an unauthorized copy of the original design, which is not conformed to the actual original component manufacturer design, model, or performance standards, and it's not produced, and there is some the specifications will be slightly and they will be defective. So there will be some alteration to the original design, and then those people will be selling at a lower cost with a different name. So like these are some counterfeit electronic parts. Some of the layers have been removed, and some numbers will be almost looks everything same. There will be small change in the number, you can see. So like overproduced parts of the foundry, some ICs are closed. Like here cloned IP to IC. They'll be changing minor changes. They'll be done, like marking indicates an op-amp from ADI, but it contains die of a voltage reference. So they'll be making some minor changes in the data sheets, some of those. Now here you can see like some of the devices, like here original device will be having gold leads, but their device they will be having non-gold leads. So rest number, everything looks similar. So of course these are one kind of attacks. I'm not discussing all. Like dual marking on one original number, you will have find something that means they are reusing, some of the ICs are being reused. Like good parts as one, like here these are some good part of the IC, and then replay the same almost looks everything, but there are 3 lines. They're showing. So photo of a suspect part. Like this is another kind of an example here, where some of the, like here you see the layers, they have removed some of this one. The pins have been, and the bend pins, the mold pin cavity is almost gone. This shows there is some kind of a tampering on this hardware. So what we're discussing is this kind of suspectable ICs we're going to use in some kind of systems. The system that security obviously you're putting at risk. the hardware or the company, suppose you're purchasing third-party IPs and you're going to include in system. Okay, so then you're putting the whole system at the security at the risk. Now these are some Intel Pentium, some of the some ICs, they have been removed and access to the inside the code. Okay, is a chip ID found after decapping, the delayering of some layers. Okay, using some invasive, and there is some IC, let us say this kind of dot indicates indicate the IC has been rejected by the wafer pattern, but some people they use for those for selling at lower price. Okay. So therefore, these are different types of components like digital and analog and discrete. These are different components. You can see the cost of this annual costing at the risk for these different companies costing in the analog ICs, microprocessor ICs, memory ICs, and you can see like here this one is analog like around 25%. The microprocessor one you can see here this one. Okay, and then the other parts and another 13% you're finding the memory. Memory is another important part of this one. So they're all costing several $1 billion to these semiconductor companies. So look at the IC recycling process. Like the recycled ICs, the ICs which are old, they looks good, but there are some they're sent to a recycling center. Which one's good one, the PCB is taken off this electronic components. Then they are produced to some kind of cleaning mechanism. They refine the recycled ICs, and then they will they resolve them as new, and then they are going to be used in some critical applications. Some normal application no problem, but there are some applications which are very critical applications, healthcare or some So therefore, there is a possibility. Of course, it's not. As you go for lower and low cost of a system, there is a possibility of this kind of attack that we are discussing. That one. It's not that every system that's going to be used, we don't doubt everything, but the underlying assumption that the hardware is secure, that assumption has to be removed. That is the reason we are going to discuss the different examples. Like here, you can see like the different counterfeit electronic components that can put millions of lives at risk. So several times you don't there are some plane crashes demonstrated. They could not able to identify what is the exact root cause of that one. So the lives of the people are quite literally depending upon the reliability of some of these electronic products. And the more introduction of some of these counterfeit components into this in the life cycle of this the hardware, so which we are putting this whole system at the compromising position. So therefore, let us look at some kind of like further kinds of threats which are possible during the different stages of the design, like hardware threats. Like there is an IP vendor. There is let us say you're going to build an SOC. Okay, SOC. What you do is that you purchase the different vendors. Then there is system integrates. So different IPs like hard or firm or the soft IPs they're purchased and then they are integrated. And then there is manufacturer. Now here any of these steps can be untrusted. The IPs, the third-party IPs which are going to usually you purchase from a third-party IP, a reliable one. But suppose you purchase from somebody, although companies themselves may be trustworthy, but sometimes the individuals can be compromised. There are big lines of code will be there. A few lines of code has been changed in the hardware, so which is difficult for identifying by anybody. The functionality remains same. We are going to look at some kind of hardware security like Trojans we are going to discuss. Okay. So somebody changes the 2 lines of a code. So it will be difficult to identify that one, but the functionality remains similar. So similarly at the system and at the foundry, somebody changes the doping concentrations or the characteristics. So that what happens, the product that's going to come will be, so that the competitor will be given more edge. The functionality or the reliability of your devices goes, and intentionally they make the devices low durable or low performing, so that the neighbor, the competitor gets an edge over that. Okay. So like the reasons for this one is like the shift in the vertical one, no one company can manufacturer. So what they do is that the design, the synthesis, placement, routing, that they were taking place at different, the horizontal, the domain, that at different globally distributed companies are going to be involved in the overall life cycle of the final hardware that's going to come. The IC, the FPGA or an SOC or a ASIC that you're going to develop. A large number of these designers and the third-party companies will be generated. Like you have, let us say, system on chip. Company X, company Y, company Z. They might be distributed across the world or a globe. They're all coming and integrating the system. Usually purchase components from a third-party, reliable third-party IP. So then the final system that you're going to build will be in a compromising disposition. Like here you can look at the ICs coming into, there is SOC design, the ASIC final. So maybe you are going to look at some of this ASIC design flow, I think, using Cadence tools in next few weeks, next few days, I guess. Some of the tools you will be going to see. Now there are, as mentioned, like there's some more like previously there are kinds of attacks called the IPs we are going to purchase, the origin of attack and where the type of attack and what it will do. Like there are third-party vendors are there who are purchasing SOS integrator. So at what stage of that one you're compromised? At the vendor, third-party vendor side, or the SOS integration side, or the foundry side, the PC assembly at the PC assembly facility, or the testing facility, or at the end user. Then basic types of these IP piracy attacks are classified into three categories. One is called hardware trojans. Another is cloning of the ICs or the IPs, hardware IPs, reverse engineering of the IPs. And now the impact that each one will be having, the goal will be, if you are hardware trojan introducing, I'll be discussing what do you mean by hardware trojan. So you can confidentially leak the information or modify the functionality, or you can perform a denial of service, although authorized vendor, authorized, but you reject accept the call at the specific time you need the particular support, you don't give that because of that you have done that. Denial of service. Then reverse engineering, you can steal the design, you can change the functionality, reliability, all different kinds of attacks you can do that. So now you can see the supply chain, as I mentioned, different stages of design, fabrication, assembly, distribution, lifetime, and recycle. You can see at different stages of that one. So there's a possibility of compromising at the different sites because a large number of third parties are going to be involved. Okay. Although the organizers themselves can be, but the entities that are going to be, the individuals going to be involved can be, okay, so can be compromised and they can be making some changes to the final. They all can be finally contributing the final, that hardware that going to use in your system can be compromised. Whether it's the performance level, or it can be the lifetime reducing, or its overall functionality can be getting affected. So therefore, we are going to look at some particular kind of attacks on the passive RFID tags here. The passive RFID tags are one of the low-cost solutions for providing the authentication. Okay, so basically they will be having like the tag, reader, communication protocol, okay, the middleware or the database. So the different types of attacks have been like demonstrated, like tag cloning, like duplicating or manipulating the RFID tag data to make similar to copy, okay, so that it can be accepted by an RFID application. Okay, and then tag spoofing, the emulation, there is a third party getting into and mimicking like it is a valid valid participant of the tag, or eavesdropping, like listening to the confidential information and extracting that, like using some special reader and antennas to collect an RFID data, and then you can use that record the messages, and you can, and either you can record or you can, so it can either direction, you can also send some signals and gain a control over the function, or you can also listen confidentially and you can silently. I'm going to show some of those. Then okay. So the tag cloning and PUFs, so some solutions were demonstrated like PUFs and watermarking, some of the solutions. Okay. So unclonable RFID tags, if you want to make the one tag unclonable, this RFID tag, one successful solution people have demonstrated to be like a PUF, which I'm going to elaborate in the later, okay, in the next few slides, the PUF technique, which is proven to be quite reliable and secure. So fingerprinting of RFID tags. So each RFID tag can have a specific unique fingerprint, which is different from the different tag in that. So how this can be done, I will be discussing using some mechanisms like manufacturing differences will be using clock skew, transient timing responses changes, or frequency response changes, some of those, and that they create one unique response. That response will be unique to the particular that tag only. It cannot be cloned. So that is done by using this PUF or physically unclonable function. Same process, same thing, but two different types, because manufacturing variations will be different. So that will capture into that. It is an example of an unclonable RFID tag. It is an RFID, okay, the floor plan, and you can see here, the most of the area is occupied with entire RFID, but a small area, if you include, let us say, using the physically unclonable function, or let us say, shift register, linear feedback shift register, LFSR, which can increase the authentication and the secret key generation, the inside it generates. So it can make the RFID tag more secure. So I'm going to touch upon the next one, hardware trojans. So as I mentioned, I'm going to introduce some different types of hardware security attacks, and then I will particularly looking at the a few particular attacks and the countermeasure solutions. So another important one is a hardware trojan. So what do you mean by hardware trojan? So hardware trojan is a malicious modification to the existing hardware, a small modification that you do such that normal functionality, entire thing remains same. So when you're going for functionality testing or manufacturing testing, there won't be any changes, and normal testing methods will not be able to identify there is an extra small amount of hardware is present. For example, let us say you have, let us say there is a kind of a chip here. A small, let us say a small small antenna has been placed. Okay, whose area is much smaller than the complete, let us say, billions of transistors there. So what the adversary can do, the adversary can send silently so it's acting like a backdoor. So the adversary is listening the data or the information, what function, what processing is done, and then a particular action to be done. The adversary can take a control over this one. Okay, can interfere with the functionality of this particular IC, and whichever is the function it is there, you can compromise that one. So that kind of attack is called hardware Trojan attack. So such kind of Trojans are usually the normal our testing methods, functionality or manufacturing testing methods will not be able to identify. We are going to see why they cannot be identified. Some examples we are going to see. So, okay, is it clear what we mean by hardware Trojan? Is it clear? Okay, thank you. So the hardware Trojan structure, if you try to look at, the hardware Trojan will have two parts. Basically, there is a one trigger part and a payload part. This is our Trojan-free normal circuit, the IC you have. Now, what you do, you add small this kind of, let us say you added small this hardware, a few logic gates. It's not very, in the billions of transistors of gates you have, you added, let us say a few logic gates you add. Okay, so what it does is that, suppose the trigger, what it does generally, the trigger will be monitoring. Sometimes the trigger depends upon when the particular Trojan should be triggered. It can be done either usually by external mechanism or internal mechanism. So what they do is that let us say that the adversary or the attacker got access to different pins of the during testing. What we do, if you want to do the testing facility, you will increase the controllability and observability. So the internal nodes will be you try to make accessible. While doing that one, so generally the testability and security are slightly at opposite side. If you want to make the testing facility easier and easier, you're actually making your system compromising at the security. Because you're making some of the internal nodes visible more and more. You're increasing the controllability and the observability, and that is giving access to some adversary to more gain control, understand your chip functionality. So let us say at different parts of the node, let us say some signals are coming like T1, TK. These are usually very rare signals. So when a normal functionality is being done, these signals will not be able to identify. So suppose all these signals are high. Suppose there is an AND gate here. Then this AND gate will be high, and then it can be changing the payload and Trojan-free circuit. The signal will be same normal, but when this gets enabled, it can be changing. I will take an example, more example. Suppose the different types of Trojans, let us say combinational trigger Trojan. Suppose these are some rare signals from different portions of the circuit of the chip, A and B. So let us say C equal to AB, it is the normal. So when A and B are high, C will be high. Okay. So there is a rare combination when A and B are 0, the C getting enabled and this function changing will be rare. Okay. So what we do is, suppose we added one NOR gate here. So NOR gate, when both are 0, so what happens? This one will be 1. Now the C signal which you are excluding are with 1. Normally C and C modified will be same as long as this trigger is not enabled. But when the signal gets enabled, the C will be now C your exclusive are with 1. When this enabled, C exclusive are with 1. Any signal if you exclude R with 1, you will get the C gets modified to C modified. So that we are introducing an error. The 0 is supposed to be there, and then you introduce error 1. So when normally testing this is okay. So this won't be happening. But because of this addition of this is one trigger, this is the payload. These two gates, the circuit C is supposed to remain C, but it gets modified to C modified. Even for the same case, A equal to B equal to 0, C is supposed to remain 0, but it becomes, because of this one, it gets toggled to and become changed to 1. And now that can trigger a particular other phenomena, and it can take control over that. So this is an example for a combinational trigger Trojan. Combination means a particular rare combination takes place, then the signal, the event gets triggered. Now another one is sequentially trigger Trojan. Sequentially trigger Trojan, what you do, you just add some, there is some sequential circuits like counter or FSM you will add. Okay. And then in addition to some other logic gates, what you do, Sequential is generally more difficult to detect than the combination. Combination only once the event takes place you will do. But sequentially, what you do, the same rare event, you wait for some more repetition. Then when it happens, then what you do? Suppose there is a counter. Let us say 4-bit counter. When the 4-bit counter, let us say the maximum value, let us say 15, 1, 1, 1, 1, all ones. So the AND gate will receive all ones high, and then it will be enabling the trigger, and then this XOR will be enabled, and the ER gets changed to ER dash. So it is a synchronous counter, or sometimes called time bomb Trojan, synchronous Trojan. Now this one is another one, is an asynchronous. Any questions?
Sorry to disturb you, Dr. Ramesh.
Yes, please.
What I personally feel is all the things that you are explaining here, they will be tested by any verification engineer by DFT. Am I right?
Yes, 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 yes.
But these things cannot be under hardware threat, if I'm right. Because when the title is, when you are talking about the hardware threats or something, it must be done by someone externally to spoil or to give some trouble to the company.
Yeah.
As far as my knowledge goes, all these things, scanning and DFT, everything, I think these are all done by at the post silicon, post layout situation. The DFT
Okay,
engineering
sir.
will do.
Okay.
Correct.
That's what I mentioned, sir. See what I'm mentioning. These are the hardware that is not there in the circuit, that has been modified by the adversary. You're understanding, sir? So this
but these
hardware
things
is,
will be tested by the DFT engineer. No, that is a whole
DFT
idea of the
means,
DFT is that. No?
yeah, that's what. This combination are rare combination. The combination, when rare combination takes place, then only the trigger. Otherwise, the trigger and the payload will not be enabled, and the signal you'll be seeing will be normal. So when a rare combination of DFT engineer tests, the functionality will be same only.
Okay.
Right. Okay.
That
so
means
the function.
Your idea is if someone intentionally introduces these triggers,
yes,
then the problem or threat will be there.
yes.
Correct?
These are the modification to the hardware. Like there is a Trojan-free circuit. There is a small. You are adding, let us say, one counter and one this one. The functionality when you're testing doesn't tell us when there is an additional counter is present or this one. Normally, when you're testing, the functionality remains same only. But these are hidden only when a specific that rare event takes place. Then this trigger will be enabled and the signal will get toggled.
But this must be done during the fabrication of the chip itself. No, once the chip is fabricated, nothing can be done.
Yes. That's why, as I mentioned in the previous cycle, some kind of Trojans can be inserted during the design phase, or maybe the third-party IP. Some can be at the foundry level, or some can be even done at the testing facility also. Whoever is having access to the actual hardware, it can be possible, sir.
Of course. Okay, right. Fine.
Okay, sir.
Please continue.
Okay, thank you.
Please.
Okay, thank you, sir. Thank you. So similarly, there are a few other sequentially triggered Trojans. So I'm not going into this one. Now, some Trojans, previous one we have seen, they are mostly digital triggered Trojans. Some Trojans can be analog, like you are seeing what you are seeing. Suppose there is a rare event. The capacitor, whenever there is a threshold value reaches, initially suppose Q1, Q2 are 0. What you have added is the gate. These are the additional circuitry you have added. Okay. The previous here you have a Trojan-free circuit. Now Q1, Q2 are 0. Normally rare combination. Normally they will be 0. Okay. So then their AND gate will be output 0 and the capacitor will be discharged. Now suppose when a rare combination of Q1, Q2 goes high. Okay. Then what happens? The AND gate will give a logic 1. The capacitor starts charging. Now when the capacitor starts charging like that and the threshold value, specific value reaches, when it identifies like a logic 1, then the XOR it will be enabled and the signal can be changed. So this is an example for an analog triggered Trojan. So you can look for more. These are from in this textbook. You can find more of this information will be there. Okay, these are actually these are not my results. I'm just presenting as an overview about some of the hardware security attacks. Okay, so please look into some of these. These are from IIT Kharagpur. Okay, Chakravarti. So they are working. So please do have a look at once. Okay. Now, these are some more examples of this one. I'm not going to. Now, these are some kind of Trojans on the FPGA. What can be done is that, as by changing some of the combination as I mentioned, the FPGAs, what you have the SRAM bit cells. They usually store the configuration cells, with 0 or 1 indicates from which block there should be a configuration of the connection. So if you can change these configuration bits of the cell, let us say from 0 to 1 or 1 to 0, so you can make the changes, the connection between you can be changing. So therefore, like sometimes what we can do, you can change let us say there is a clock manager is there, particularly some of this one, you can increase or decrease the clock frequency. Okay. So that you can introduce some kind of timing errors, but these combinations are very rare, such that they are generally not caught during the normal functionality. For a normal functional test, generally it's done exhaustively, but it is for the present generation of complex ICs you have, suppose you have a let us say you're doing a 32-bit, let us say, adder. 32, 2 power, you have 2 power 64. Even if it's generating, let us say, generating, it takes several years to complete all the inputs to take. So you're only checking only a few combinations only you'll be testing. So there are possibility that some of the combinations gets mixed there, and we can so normal manufacturing testings or functional testing are not able to identify some of these kind of Trojans. So this is a classification of different kinds of Trojans, and like at what stage you have insertion phase, whether there's a possibility of changing the specification, like changing the temperature, design phase or fabrication phase, or testing or assembly or packaging. So at what stage you have inserted this one, then at what level of abstraction you can insert this Trojan. So these are all classification based on like whether you can do always on or triggered like internally or externally. So what effect it will have, whether only changing the functionality or degrading performance, or able to like leak information or denial of service. And what location of the you're doing that, this kind of inserting the Trojan, whether a processor or a memory or the IO pins. Like suppose sometimes at a particular time it's worked like an IO input, IO programmable IO pins will be there in the FPGA. It's supposed to act like an input, but you change it like an output by changing the configuration pin. So there will be high current flowing from the input output, and the device, external device, can be affected. So some of the physical characteristics. And these are some of the countermeasures possible existing hardware Trojan countermeasures, like Trojan detection techniques. Okay, there are some Trojan detection techniques are there, and some countermeasure techniques. Here, some countermeasure techniques I'll be discussing. Like one is a logic obfuscation. It is a quite well-known technique. So please have a look at more this from this textbook. Okay, so logic obfuscation. Generally, any attacker that wants to attack the particular device or the circuit or a system, they need to have some understanding about the system. They need to observe its functionality over a period. Then only. So logic obfuscation, what it does, it tries to mislead the attacker. So the function, it is one function, but it misleads. It looks like another one. So it will obfuscate the attacker, so that the attacker will keep oscillating in one kind. Let us say there is an FSM is there. You add some additional kind of, let us say, states you have added. You add some additional states by obfuscating. Only when it's when the specific key is given, then only you can come to the normal function. Else the attack, let us say, keep moving in the same block states only. So therefore, only when a specific key is given, then only you can come to this one. So that comes under logic obfuscation techniques. Like here, there are a few techniques. Like this is one technique, like camouflaging. It is a layout-driven technique. So it's a layout for a 2-input NAND gate and a 2-input NOR gate. So what they do is that they add some. Of course, it is not a general standard procedure. Of course, by doing this one, you're making some changes. This method actually is not good for a standard cell layout. The design process gets complicated. But some tools, if they can support that kind of, okay, so that will be done. So what they do is that they try to confuse or mislead the attacker. So when just by looking at earlier by standard cells, if you look at the standard cells, by looking at the layout, okay, you can understand is an AND gate or NOR gate or some basic standard blocks you can understand. But now what we'll do, both look similar, and then they'll be confusing by making some changes to some dummy contacts and some faking connections. Okay, so by making the changes, so it will be misleading or obfuscating the attacker. So it makes the job of the attacker difficult. That is the intention. Now there is one more technique, like it is there in the 3D IC techniques, 3D IC technology. Like it is split manufacturing. What they do is that the part of the layout they send to one foundry, and the another part they send to another. Then they integrate and then do. So what they do is that they minimize this possibility of tampering at the foundry side. So part they send it one place. So this comes under split manufacturing. So these are some successful techniques have been demonstrated. Okay, so they have been existing. Now some techniques like like watermarking, as I mentioned, the IP thefting is taking place. So some people were looking at the watermarking of some of the IPs, hardware IPs. Okay, like using metering, the active metering or passive metering. Like this is one layer, adding a lock to the hardware. So normally it gets locked. Only a specific key is given, which is available with the particular the owner of the IP. Then only the lock gets open. The functionality will be okay. So these are some kind. Like here you can see some kind of, there is a demonstration of the watermarking that has been demonstrated in one of the Apple computers. So that was demonstrated. You can have a look at this one more. So as I mentioned, some techniques against this watermarking obfuscation and multiple small watermarks. You can give multiple such things. Parity in watermarks. So this one. So coming to this one, side channel attacks.
Ramesh,
I
could not understand. What do you mean by hardware? In hardware watermark, what do you mean by that?
Here,
watermark means here in terms of hardware.
Your hardware watermark, sir. They will add one specific hardware marking the vendor to whom the particular device has been sold. Okay, which is store in the inside of the memory device that going to use. So the tag will be deciding to whom that was
sold.
It's
a tag. It's a kind of a tag. That's it.
Yeah, it is an authentication, and also it's like so it's actually similar to like digital in the images that you use, digital watermarking you do in the images. Its concept is similar to that one. Your hardware metering is a similar concept here.
Achha, one more thing, just before you continue next thing, what Dr. Murthy just he has asked. No?
Okay, sir.
Yeah, he was Dr. Murthy, so related to that only. So by putting this kind of techniques, don't you think we are making a job of DFT engineer or testing engineer difficult?
Yes, I agree. Yes, that's what I mentioned. Security and testability are at contradictory at present. To make the job of the testable easy, what we do is that we increase its controllability and observability. We try to increase it. But by that we are actually compromising security. Therefore, what we need to do, there is an optimal kind of a solution has to be generated. So that means the tools that we are going to use have to be changed. So whatever the conventionally the DFT techniques we are going to follow, that's not going to work anymore for the long. So if you want to take the hardware security seriously, so the researchers and the industry, they need to start relooking at the way this testing is done. So all these things, that's what is being communicated by this group of researchers. So definitely that's going to make difficult. You're deviating from the conventional flow, the standard cell flow. If you're changing the layout or if you're changing, so you're making the job of this, so definitely you're making difficult. You're deviating from the conventional path. So therefore, the novel, that kind of those CAD tools platforms and design approaches. So just like design for testability we have. So recently people are claiming like there is a design for security also. There are some blocks they're going to put exclusively for design for security. So that makes the job, I think, slightly easier. So the testability and security simultaneously can be done, accomplished. Is it clear, sir?
Yes. One more thing, actually, I could not understand when you said that the designer or let us say I'm designing my IC. Why do I put the Trojan in my design itself? Because you said.
Not sir. Sir, you don't put. Suppose you're making a system, you're purchasing some third-party IPs from let's say different vendors. Obviously, you purchase from credible third-party IPs, but there is a possibility of compromising the IC at that particular, let us say that hardware IP that you're going to either whether soft IP or the firm IP or the hard IP you're going to purchase. Okay, so there is a possibility of the tampering is there. That's what is mentioned. So
okay. Now I understood. That means if I'm not getting the complete manufactured IC, it is basically a design IP which I'm getting, and then I'm introducing those Trojans into that.
Yes, sir. Like suppose you're making an SOC, sometimes the entire processor or memory you can purchase, or maybe let us say some security module or something. Then you integrate and you build your own system.
Yeah. Got it.
So then there is a possibility of tampering done at the vendor that you have purchased. So generally that's why mostly there are uses of open source tools has to be done with very carefully. The open source tools that we are going to use have to be done very, very carefully. Open source tools or platforms.
I think Murthy sir also clarified hologram. So one more question is there in chat box. I'll wait for you.
Yes, sir, please.
How hardware metering can be used for PCBs?
Hardware metering, PCB protection.
Who has asked? Ashwini madam. Yes, she said yes.
Hardware metering, if you want to PCB change, you want to include extra small component for doing that one, sir, or the PCB you want to change?
Sir, you have said in that slide that the same technique can be used for PCB or IoT devices. So can you please focus?
Yeah, IoT device, as I mentioned, here particularly I'm talking from the final chip that's going to be the designed and manufactured. Then the IoT device, the hardware can be, there can be PCB, there can be different active passive devices, and the ICs also can be there. So here particularly now I'm talking about the FPGAs that we are going to design. Okay, the FPGAs you are going to take are the ASICs that you have. So how to secure? These are some techniques that are there. So the PCB, if you want to make, so the technique, the PCB technique, if you want to do, so then what we do, we need to add some additional module, like maybe some PUF or TRNG to make it secure. So we need to add the authentication to do that one. So because you cannot change the layout of those, the device, those things, so you can use some of those techniques. That is it clear, madam? Okay, thank you. So now there is one more kind of attack, like side channel attacks. Okay. So I'm going to little slightly speed up on. So side channel attacks. So you can see that the different applications that we are going to see, the cryptographic devices. They use some cryptographic algorithm and store a cryptographic key for securing the particular transaction, whether it is an identification or a payment or a communication multimedia. So that is different digital application that we are having. Okay. So but they are exposed to adversaries in a hostile environment who have full access to the physical device, that one. So therefore, the adversary might be, sometimes what happens, the adversary might be a legitimate user also. There is a possibility that the adversary or the attacker may be the legitimate user also, is a possibility is there. So the conventional security problem thought to be like this. The channel is the only place people used to think that this is where the attacks going to take place. So they wanted the whole focus on this one. But now it has been demonstrated that needs secure implementations, not only the algorithms or the protocols for between the communication between the two, the devices that we are going to use also needs to be securely implemented. So that is the what we are discussing here. So therefore now let us say there is a cryptographic algorithm is running on a particular system to secure your using. So the physical attack that they are not exactly same as crypto analysis. Suppose the side channel attackers, what they do, there is a particular input and there is an output coming. Instead of directly looking into the particular algorithm, understanding that one, so what they do is that they try to observe some side channel parameters. So some parameters which are in the vicinity or the environment of the device. From that, they try to do a further information analysis and they try to extract the key from that. Okay, the key which is stored inside this. So from that key, they try to extract the functionality of that one, like some kind of side channel emissions like power consumption, because logic circuits typically consume different amounts of power based on their input data. Just like suppose you take a 2-input NAND gate or even NOR, let us say inverter. So the 0 to 1, 1 to 0, the power consumption will not be same. Similarly, NAND gate, if you try to see anyone has done any NAND gate, let us say transient characteristics, you try to do, try to draw the transient current plot, just see it. The current as a function of time. At 0 to 1, 1 to, it's see at different time, the current spikes will be different. For every case, it will not have the same. So that what some of these attackers they have demonstrated. So they can, by getting the different traces of these current traces and the different they observe for over a period of time, they extract that. They're using some kind of, particularly this task can become much easier if you use some machine learning kind of algorithms. Earlier it was slightly difficult, but now using some machine learning kind of algorithms, the task has become, it has slightly more simpler. So the analysis will be easy and you can give the conditions and you can extract that parameters. So some of the side channel attacks, they aim at side channel inputs and outputs, bypassing the theoretical strength of the cryptographic algorithm that is there. Okay. So suppose just I mentioned, you see here you don't see then only the average power over time or the peak power. You try to see the instantaneous power over time, and a different samples will study over different period of time, and then the data you'll analyze, okay, and then classify, and you can say this is the particular combination, this particular input, and you will try to understand the system behavior better manner. So that is giving open to the door for this kind of attacks called power based attacks. So they're making some changes to, like, suppose there is a pin is there. The pin, you let us say, of course, some attacks are, sorry, like some attacks invasive. You need to change, like you need to introduce one kind of resistor at a pin you connect. Okay, then try to power supply is fixed and current you will be changing, and then as I mentioned, the oscilloscope will be capturing the current waveforms. These waveforms you send to, let us say, our laptop are there where you do the algorithm where you have for the further analyzing and classification. Sometimes okay, there are some algorithms have been written so for doing that one. So that will make, like example you can see here, the basic measurement, constant supply voltage. So the current only varying. Okay, so if you can get the current waveform, you're actually getting the power consumption waveform. Okay, so in CMOS technology, the static power is almost very negligible, very small. So the dynamic power is the most one, and it at different times the power consumption will be different, as I mentioned. Suppose input is changing 0 to 0 and 1 to 1, the current will be very small, as I mentioned. Suppose input is changing 0 to 1, output will change from 1 to 0. So there is a discharge will be taking place. 1 to 0, capacitor will discharge. Now 1 to 0, suppose input changing, output change 0 to 1. So there is a charging. So this is the energy consuming transition. When it is charging, draw from the power from the VDD, the current will be drawn. So 1 to 1 and then 0 0. So the current waveform will be varying for different cases. So therefore, the user tries to give different inputs and tries to for different inputs he tries to understand the different combinations and the traces he will try to extract, and then they try to analyze and they try to extract the key that is there. Okay, particularly we'll try to take some examples of the some encryption algorithm that we are going to see. So there is one particular researcher, they Ketchoffs, okay, they made that the attackers won't, almost all of the data that is required to operate a chip is entirely hidden in the key. So the attacker only needs to extract the key. Okay, so they can extract the key, then the necessary information to understand, so that will be done. So what we do is that basically using a divide and conquer approach, the parts of the key will be extracted in a divide and conquer manner. Okay, for a given different combination inputs you will give, and then try to extract part of the key, then it will be verified. Then you keep repeating that one for the rest of that one, and we'll try to get extract that one. So this is being reported. This has been reported first time like by Kocher in 1996 on one of the encryption algorithm. It has been done. Okay, the simple power analysis, they try to extract it, and then they try to get for the different, and then the zoomed input of these few rounds they observed that, so they are able to extract the key of that one. So the countermeasures is that suppose if you can de-link the countermeasures, or solutions possible is that when you're extracting, you introduce the decorrelate. So if you can make a structure like decorrelate the relation with power signal versus the switching activities, then the user will find it difficult. Like in VLSI, like there is a differential cascade voltage switch. The differential topology, the power consumption bit you will not be able to see because of the differential nature of the signal. So that's why that can be hiding the details of that. The power consumption, but just by looking at the power trace or the current trace, you cannot say which kind of function is running. It will make difficult. You need to make it difficult. That kind of algorithms will make the that function secure. So therefore, coming to these physically unclonable functions. So as I mentioned, so the conventionally what we do is that for authenticating the devices, generally the key is stored on the device itself. Okay, the private key is stored on the device itself. So the because the device will be stored. So therefore, it has become easy. Recently there have been demonstration. The key can be extracted. The key, it is not secure to store the key in the device itself. Okay, there is a key, and in the memory, in the EEPROM that you have, the key you are storing, particularly the decryption key or the device to extract that one. So therefore, it is authentication. For the authentication purpose you are using, but you are compromising on the integrity or the privacy of that one. So therefore, only the software NVM based techniques are not working. So there is a demand. So therefore, they try to make whichever is the data, they try to more secure more and more by using some costly mechanisms like that. They try to, there is a processor, secure processor which is a secret key. They try to tamper-proof package. They try to use it is a very costly, expensive mechanism. So there are some modules also earlier used like hardware security module, some trusted platform modules. Earlier they were used in some of the Intel processors, etc. But the drawbacks with some of these were is that there is a possibility of extracting the key was there. So therefore, the designers have looked at, is there a possibility to use some other? There is always a parameter variations are there in the device during the manufacturing. If you can extract the parameter variations and use it like a feature that we can save we can authenticate the device. So therefore, there comes this device called physically unclonable function. So there is a physical system. Then there is the physical system. What is there? There is some challenge bits you'll give. There is a response. The same device at different time, if you give the challenge, the response pace will be varying. So what happens is that the physically unclonable function is based on a physical system and it is easy to evaluate, but output looks like a random, but it is okay. But there is some, of course, there is some correlation you can extract. So what we do is that the non-volatile memory is that one, the extra processing steps, and generally the physical attacks are vulnerable, so the data can be reprogrammed. But the physically unclonable functions, they have some advantages over this. You need not store the key there. The key will be coming in the form of a small circuit that will be adding, and which will be the variations in the device which are unpredictable. Those you are using to generate a small kind of an authentication for a particular challenge, you give a particular response comes, that will be authenticating this particular device is the authorized one. So the standard CMOS process will be used. Okay, and also it makes the difficulty of cloning or attacking, it makes the difficult. So what you see is not what you get. The function looks similar, but what you get is different. Okay. So there is some circuitry to add to, therefore there is a mismatch, and then digitize and stabilize, and these correcting circuits will be there. These are the different stages in the PUF design. This is an example of a PUF design. Like here, there is an input coming. There are different paths here. Now what we do is that the paths you connected in, let us say, you have connected in this arbitrary manner. So the delay will, now there is a challenge you are giving here. Suppose let us say there is a 64 bits. Depending upon the different challenge bits you will go, you will be giving the paths will be varying, and because of the manufacturing variation, the delay will be varying. So therefore, the signal that you will have will be different here, this one. So what happens is that, so what you see is not, okay, what you get is different from what you see. So that's what you're using this in the silicon PF. So there only a particular challenge comes, a particular, the PF will be generated, and then the device will be authenticated. So that is used for device authentication. Like these are some demonstrations of using for some TSMC, different chips have been manufactured using the same process. Then they try to estimate the probability of what is the repetition or the uniqueness of that one. They observe so there is a 50% of the, this is one is called uniqueness, another is called reliability or reproducibility. These parameters have to be satisfied. Then you can say it is a more reliable and secure PF design. Okay. So then another solution is a true random number generator. So that it is an extension of the pseudo random number generator, but here use the some of the random number phenomena will be used. There will be entropy source will be there. The entropy source, there will be a harvesting mechanism, and then post processing. So generally, so the requirements for any TRNG will be the design should be preferably digital. The harvesting mechanism should be simple and very low. There should not be any further correction circuits, and the design should be very compact and efficient. The design should be sufficiently simple. Okay. So one example is using the clock jitter. So jitter is variations in the significant instance of clock, and jitter is generally is not deterministic, it is random. So that randomness in the clock jitter has been exploited using a circuit, okay, using a circuit topology to translate to generate a unique number, which will be useful for this authentication. So this is a typical structure, general structure. There is a, let us say, a LFSR will be there. There are some ring oscillators which will be using the process variations. Then there is a selection and operation. There is a operation unit will be there and a capture unit. Okay. So so what happens is that the final number that is coming will be a random number, which because of the randomness coming in, this one has been exploited. It is generating normal one. Okay. So therefore, this is the last topic of discussion, as I mentioned. Now I will try to demonstrate one PUF and TRNG demonstrated using one of the transistors, like tunnel transistors. So I'm trying to move it. So here the post-CMOS technology based TRNG, like here this is a comparison of energy. These are the data from the literature, but this is one paper which is under review. So it's on the second review. So we have this is data from our paper only. So we try to have a comparative study of the energy consumption versus area of the different of the emerging some of the devices. Similarly, bit rate versus error, energy consumption per bit. So normally the devices which are more preferred will be smaller area and smaller energy consumption. They are the most desirable candidates. Okay, you can see the most of the CMOS devices are in this part of the spectrum, and the more emerging devices you can see they have more some better candidates, like particularly STTP3 kind of thing. Okay, similarly tunnel FET, they have some interesting characteristics are there demonstrated. Similarly here energy consumption picojoules per bit and bit error rate. So bit error rate should be as small as possible. Okay. This is a comparison about the the bit error rate, uniqueness, and some the features. Different devices, they have different characteristics they have used to perform a different kinds of an attack they have demonstrated. Okay, some they try to demonstrate for a side channel attack they have demonstrated. Some people have demonstrated some kind of a PUF or some kind of a TRNG demonstration. This is for the PUF matrix comparison. Okay, like you can see here. There's some, this data is not available, so we could not put it. Like STTP3 devices, based devices, they have some general uniqueness should be close to 50%, and these devices are like you have the bit error rate, it should be smaller. You can see the STTP3 based devices have been using side channel attack prevention, they have demonstrated. So these are the comparison about the different demonstrations demonstrated, like 128-bit AES has been demonstrated, some SCA circuit they have done, okay, some enhanced DPA resilient circuit they have done, like, okay, so there's some Kasumi algorithm they have demonstrated some of these using some of the emerging devices, and they demonstrate some of the energy consumption and the area of overhead. This is for the like hardware obfuscation techniques, the different characteristics in each one of the device they have tried to exploit. Like silicon nanowire FETs, the tunable polarity of the characteristics they explain. Like in tunnel FET, we are the first people, like we are done using this tunnel FET characteristics to demonstrate for the security demonstrations we have done. Similarly, some people have done using this PCM devices, phase change materials, and STT device. Some people have demonstrated, and these are the results comparing like the area enhancement and the key enlargement they have demonstrated. This is a further summary of this one. So I'll be sharing. You can have a look at more. Some TRNG, PF, and some of these things have been demonstrated. So now, based on this, what we have done here, the tunneling transistor FET has some unique characteristics. We try to explore the unique characteristics, like suppose this is the device when it is like when it is off, the device is off. Like when it is enable is on, the input 0. Let us say it's an inverter. This is inverter. Let us say 1 you give here, inverting 0 comes. Then depending upon the path, this is a transmission gate switch. It should be driving the load capacitance. No, so what happens when the device is when it's off, because of the pin forward leakage current in the device, what we have observed that there is some amount of current is flowing. So what we have done, current we try to control the device. That current we try to control, and then we designed one kind of this delay line has been demonstrated. What we have done is that normally the design shows that it has been designed for 50, the expected oscillation, let us say 50. But the design the delay that it depends upon there is a parameter that controls the current in the reverse, that one. By changing that current, only one who has knowledge about the device will be able to understand what the particular circuit is behaving. Otherwise, just by looking at the circuit, anybody understands. Let us say it's the 6-bit counter in this one design. It has been designed for 50 count, oscillation count. But as we have seen that the oscillation count, because of this one we have introduced, and the parameter that we are controlling, at different times of this one, it's producing different oscillation, the same circuit. So in this manner, we try to use that one to generate a complete random number generator, and we try to estimate its functionality. So it has demonstrated a good, we try to compare the bit error and power consumption, and try to save the, so very low power consumption and a reasonable amount of the bit error has been demonstrated using. And of course, at very, very small supply voltage, like we have demonstrated 0.5, similar to CMOS oscillator, okay. So you can see the number of gates, we have used very less gates, and the bit rate almost like equal to CMOS, we got it here. Of course, as I mentioned, these are all simulations. Now, this is another like differential power analysis. This is an FMOX. With and without, we are trying to extract. Now, the trace which has the correct key, that comes outside here. The correct key. Okay. The correlation coefficient shows that the correlation coefficient, the way you do it such that whichever is the correct key that you guess, that the correlation coefficient, that key will be outside. So that indicates the key that you have guessed will be the correct one. So these are the power traces of that one we have generated this one. So therefore, as we have seen, the CMOS technology scaling, with the increasing the CMOS technology scaling, so there is the hardware security and the increasing problems with the hardware security. Just relying on the CMOS security itself is not adequate. So therefore, researchers and industries, they are looking at different alternative post-CMOS devices for demonstrating exploring their unique characteristics to build some more circuit primitives like STT-RAMs, RRAMs, okay, phase change memories. So some of these devices are in the more front end, okay, then tunneling FETs, etc. So therefore, you can combine the device features, the emerging novel device unique characteristics, the circuit and architecture, some of the design techniques. If you can combine, we can build some more better solutions for building and enhancing the hardware security, like we demonstrated like PUF, or some TRNG, simultaneously achieving a reasonable and optimal energy efficient solution also can be achieved. So that's what the this particular discussion that we can conclude with this. Okay. So thank you all for your okay, so these are few links that people interested can have a further look at. Important links for different research groups that are working here. University of Florida. This is what I have taken some of the slides, like Trust Hub. Okay, different. There is a Spark project that is running in the UK. Then there is a different groups working. Counterfeit IC. Okay, NSF sponsored in USA and Singapore. Some of the companies which are working. So please feel free to explore more. So it's only what I've done this recent analysis. So these are some recommended videos that you can have a more look, try to understand better about this hardware security. You will have better understanding. Okay, what is inside a microchip, and zoom into a microchip and public key cryptography. Okay, counterfeit electronics could be there. So there's some videos that are there quite well presented, so you'll get some better understanding of that one. Okay, thank you. Any questions, any clarification, anything?
Anybody has any question?
Dr. Ramesh, I have a query. I would like to know that in order to build this security-based, circuits, that particular chip has to be in that. Let's say you were talking of tunnel FAT. So
Yes,
the whole circuit, the application has to be in that new, nano device, right? The emerging nano device. The whole circuit has to be based on that.
yes, madam. Okay.
Yeah. So then there are like challenges with this new technology. So because tunnel FAT has been since years and still not made it to the market, right? Is it true?
Yeah.
Or?
True, madam. I agree, because these are some circuits we had done couple of years when the tunnel transistor FETs were like quite in demand, and Intel was investing and a lot of research was going. So at that time we had done some circuits like past couple of years. It is a part of a project. So I do agree that tunnel transistor FET has reduced recently. It's actually like experimentally it's having some issues are there. Particularly the on current and subthreshold swings. So I do agree with that. So these are all simulation. As I mentioned, these are all simulation results. These are not experimental data.
No, yes. I understand. So any emerging device, this is applicable, right?
Yes, it's true for any emerging device, madam. Yes.
But then same thing, why not to this nano CMOS or MOSFET? The same approach.
No, CMOS is not an emerging. CMOS is already in the has been used for quite number of years, and obviously any technology.
Electrical parameters. Sorry, sir. These electrical parameters that we are trying to use it for as a key, right?
Yes,
that can be applied to this present technology also. CMOS, nano CMOS.
Yes, madam. The techniques are actually these are all demonstrations based on CMOS. Those same techniques we applied using some tunnel transistor and try to demonstrate using some unique characteristics in the device. That's all.
I see. But there is a benefit. The new technology has its own advantages. That's what you mean.
Yes, madam.
I get it. Okay, thank you.
Thank you, madam. Mrs. Somebody has some chat message, has a question.
Dr. Ramesh.
Oh, yes, sir.
First of all, I thank you for giving a wonderful, informative webinar. But I have a small doubt. When I was in long back industry, people used to say that once a person tries to change any parameter or try to include into the chip altogether goes out of working stage.
Yes, sir. There are some self-destructing phenomena will be there. Some will be there. That is one of the security features. Yes.
Yeah, that's right. So because I also found that most of the Intel chips are actually following the same rule in the recent process also. If that is the case, if that is the case, then the security concept which you have explained may be more concerned with the software concepts of cryptography, etc., rather hardware. Am I true or not?
Not exactly, sir. So what actually I would like to conclude, like the basic assumption that the underlying hardware is very secure. The entire focus was on algorithmic development of the side only, like either network security or information security or the software security. So what these people, the particular group of people, these are working like, they are mentioning the underlying hardware cannot be taken for granted. There is a possibility of tampering can be happen at the different cycles. So now what the Intel is doing is one particular technique, but So always there is always they have been demonstrating that those are not sufficient. With the increasing level of the access people have and the security adversaries, the device is going to be used in like areas the people have constant update. Like suppose you have a side channel like side channel attack kind of thing.
Yeah.
So people can access and they can the security feature can be bypassed actually. The encryption or whatever the feature can be bypassed and they can extract that one. That is possibility have been demonstrated.
Okay, fine. Thank you.
Okay, thank you, sir. Someone has a question. For extracting correct key, we need to have actual key as reference key. Is that right? Yes, that is true for the normal, like the non-volatile memory-based device. You need to store the key there. So therefore, the attacker can retrieve that key and then he can use that one. But now, instead of that key storing inside, the physically unclonable function, there is a which exploits the manufacturing variations in that using the circuit topology that you are going to design. So then you can, the key you are not storing, the key will be generated that one. Okay, then you can compare with the database, whoever has the particular challenge, the particular response pair comes, then that can be validated. Okay, so in that manner, you are not storing key there. So that is true what you said for normal non-volatile memory based devices, but that is not true for PUF based kind of a system if you are coming. So if you come for a, let us say RFID using, let us say PUF, then the key storage concept will be different. You don't need to store the key there. Is it clear? So, okay, thank you. So any questions, any clarification? So actually, these are all some recent actually learning. We are actually, some of the topics I have worked, but some topics, of course, I try to get an overall view here given. So some topics I still have not gone into deep, I have to admit here. Some topics are like like hardware security also there is quite, has been hot for a couple of years, larger number of people are working. So only few domains I'm trying to right now working, but I try to give an overall view and then few techniques we are working on that. Using some emerging devices, that's what. We are also looking at some demonstrations of hardware demonstrations also. We're trying to go in the couple of years. That's we are planning that. So we just started recently only this work. So I'm also just like initial stage like many of you here. Okay. So if you have some very good ideas, so please do get back to me and we can have take things forward. Okay. Thank you. So hope I could make you time work. So it is quite evening time. It's all of you. Okay.
But I don't think there are any more questions. So thank you, Dr. Ramesh. Thank you very much.
Thank you.
The topic, I had given the topic to Dr. Ramesh that since it's a mixed signal VLSI design kind of a track, so we wanted an advanced concepts and kind of a training program. That's why I can understand that sir has covered from devices to architecture, everything. Sir has tried to give us the how to secure our hardware at the device level, at the circuit level, at the architectural level. All entire theory he has actually tried to cover in 2 hours. And he has also shown us the work which he on himself carried out during his career. So thank you very much, Dr. Ramesh, for this entire session.
Thank you, Radha, sir.
Starting from basics to the advanced, and I'm sure not only about the basics, but there are few participants in the list who are probable research scholars. So there are so many ideas which you have given for their prospective topic. I could sense that there could be so many topics which of your this informative talk of 2 hours, and if they are listening carefully, I'm sure they should grab this opportunity. So thank you very much, Dr. Ramesh. Thanks, and this is a kind of a virtual certificate we call it, or virtual memento. Kindly accept it.
Thank you, Radha, sir, for this opportunity. Okay. Thank you all the participants. Okay, for their patience and understanding. Okay. Thank you.
Okay. So participants, I have shared the attendance list, attendance link in the chat box. You please fill your attendance as well as feedback. And as usual, you know, we always have a assessment on the next day. So based on today's discussions, few simple questions will be there in the quiz, but my sincere request is you please attempt it. Okay, do not miss it. Give an attempt between 8 a.m. to 10 a.m. Appear for half an hour, 30 minutes. And those who are new participants today, I think we have all are having good participants. Hardly 3 have joined, 2 have joined the new. So their Moodle accounts have already been created. You go to Moodle, whichever resource person is giving me the data or their slides, I'm going to upload entire course material on Moodle. So you will get the course material on Moodle. Okay.
I will share the slides.
So thank you very much. Yeah.
Okay, Rathur sir, see you sir.